So imagine a doctor, right? Someone like Dr. Christophe Delong, who's a specialist in biomechanics. And he's looking at a readout from an AI system called Kinexa.
Yeah, Kinexa is a genuinely fascinating system.
Right, and this AI has just analyzed a single fleeting footstep from a patient and instantly diagnosed a complex neurological condition. But here is the really critical part. It doesn't just give a diagnosis and, expect the doctor to blindly trust it. It actually prints out a perfectly logical, mathematically traceable map of exactly why it made that diagnosis.
Which is incredibly rare right now. I mean, we are living in an era where AI is essentially a magic black box. It gives us answers, but it cannot explain its own reasoning.
Yeah. Right.
So building a system that can actually show its work in a way a human doctor can understand and verify, that's one of the hardest problems in technology today.
And so today, for our deep dive, we're exploring the invisible mathematical tool that is making that transparency possible. It's a revolutionary concept called wavelets, or ondulets as they were originally named in France.
That's right.
And our mission today is to take you through this fascinating document that tracks these wavelets from their raw mathematical mechanics to their role in systems like Kinexa, and finally to, honestly, a wild philosophical twist about the absolute limits of human language.
Yeah, the philosophy part is wild, but we really need to start by understanding the mathematical wall we hit about 40 years ago.
Okay.
Because for a very long time, the old guard of signal processing was the Fourier transform. It's a brilliant, century-old mathematical tool designed to reveal what frequencies are present in any given signal.
So if I'm playing like a continuous droning note on a synthesizer, the Fourier transform is going to map out the exact frequencies of that sound perfectly.
It will, yeah, exactly. But the real world is rarely a continuous droning note. I mean, the real world is messy, it's abrupt, and it's dynamic.
Right. It changes.
Exactly, and that is where Fourier hits a wall. It is phenomenal at telling you what frequencies exist, but it is terrible at telling you when they happen.
I always think of the Fourier transform like a blender. Like if I throw a strawberry and a banana into a blender and turn it on, Fourier is the tool that can taste the smoothie and tell me, there is strawberry and banana in here.
That's a great way to put it, yeah.
But it has absolutely no way of telling me when the strawberry was dropped in versus the banana. It just sees the overall mixture.
Right, that blender analogy works perfectly because Fourier requires you to look at the entire signal over all of time to figure out the frequencies. So it becomes completely inadequate the second you are dealing with sudden, short-lived events.
Like what kind of events?
Well, a sudden click on an audio track, or a heartbeat, or a massive, unexpected spike in the stock market. Fourier sees all the ingredients over the course of a year or a minute, but it completely loses the timeline.
Got it. To put another analogy on it, if the Fourier transform is like this powerful telescope that looks up at the night sky and tells you the overall chemical composition of a galaxy's light over millions of years, wavelets are an adjustable microscope. You can zoom in to find specific tiny events as they happen.
Exactly.
So if I'm listening to a symphony, Fourier gives me a list of every single note that was played that night, all mashed together. But wavelets are going to tell me exactly when the percussionists crash the cymbals.
Right. The wavelet provides what we call a complete time frequency analysis. It pinpoints what frequency occurs at what precise moment. And this ability to localize events in time, it just fundamentally changed our approach to data.
Wow.
But to understand how it works, we have to look at the three mechanical components of a wavelet. The first is the mother wavelet.
The wavelet.
Yeah, this is your base mathematical template. It's just a brief, localized little wave that starts at 0, oscillates up and down a few times, and goes back to 0.
So it's just a really short burst of a wave, like a stamp or a template.
Exactly. Then we move to the second part, which is translation. You take that little mother wavelet template and you slide it along the length of your signal, say an audio recording, to analyze each specific moment in time.
Like taking a sliding magnifying glass and dragging it across a line of text, just looking for a specific word.
Yes, and we call that sliding process local correlation. The machine is taking a sliding window and performing a mathematical operation to see if the real-world signal resonates with our wavelet pattern at that exact specific moment.
Wait, what exactly do you mean by local correlation and performing a mathematical operation? Like, what is the machine actually doing when it slides that magnifying glass?
It's performing something called a dot product.
Okay.
At every step along the way, the machine multiplies the values of the signal by the values of the wavelet template and then adds them up. If the signal goes up exactly when the wavelet goes up, and goes down exactly when the wavelet goes down, the resulting number is really high.
Oh, I see.
Right, the mathematical way of saying, hey, I found a match, and if they don't line up, the number is close to 0, meaning no match.
Okay, so we have a template, and we are dragging it across the data, multiplying the numbers to check for a match.
But dragging a fixed template isn't enough to capture everything. And that leads to the third part, which is dilation. You can mathematically compress the wavelet, squeeze it tight, or stretch it out wide.
Oh, think of it like an accordion.
Right, yeah.
If you squeeze the accordion tight, you get rapid, high-pitched, sharp notes. Squeezing the wavelet lets the machine catch really fine details and high frequencies, like a sudden click or an abrupt edge in a photograph.
Exactly.
And if you pull the accordion wide open, you get long, slow, deep notes. So stretching the wavelet lets the machine see the global trends, the low frequencies, like the slow-rolling background shapes in an image.
That's exactly how it works.
Yeah.
And, the history behind how all this came together is honestly just as fascinating as the math, because
Right.
it spans a century and crosses completely different disciplines.
Right. Our source document gets really into this.
Yeah. The very first conceptual foundation was laid in 1909 by a Hungarian mathematician named Alfred Haar. He created a very simple, blocky version of this concept. But the modern version didn't happen until the 1980s. And it didn't come from a university math department. It came from an oil company.
Which is wild.
Yeah.
Jean Morlaix, a French engineer working for Elf Aquitaine.
Right. He was shooting seismic waves into the ground to figure out where the oil was. And the echoes bouncing back from the Earth's crust were incredibly messy, just full of sudden geological shifts.
And Fourier wasn't working.
Fourier was completely failing him because he needed to know exactly when the echoes were hitting to map the depth of the oil. So he essentially invented the modern time-frequency approach out of pure engineering necessity. And he's the one who coined the term ondelette, which means little wave.
So an oil prospector literally invents the math that will eventually power our phones and AI. That is amazing.
He had the intuition, but he needed rigorous math. So in 1984, Morlaix partnered with a theoretical physicist in Marseille named Alex Grossman. And Grossman gave the intuition a solid mathematical framework. Shortly after that, a brilliant mathematician named Yves Meyer, who would actually later win the Abel Prize, stumbled upon their paper.
By accident.
Pretty much. And he realized this wasn't just a clever trick for finding oil. It connected to deep foundational mathematical theories. Meyer proved its vast underlying structure.
Wow, so we have an oil prospector, a theoretical physicist, and a pure mathematician.
It was a massive cross-disciplinary effort. And then Ingrid Daubechies took this framework and created specific, highly practical wavelets. Her work is actually the engine behind the JPEG 2000 image compression format.
Let's talk about JPEG 2000 for a second, because this is where wavelets really show their power in our everyday lives, right? Because older image formats use something closer to Fourier. They broke images down into rigid 8x8 pixel blocks.
Right, the DCT blocks.
Yeah, and if you compressed a photo too much, you saw those ugly, blocky squares everywhere, especially around the edges of objects.
Because the older math was just terrible at handling abrupt changes in a signal, and the edge of an object in a photograph, say, the dark edge of a building against a bright blue sky, that is a massive, abrupt change.
Yeah.
But wavelets, because of that accordion-like dilation we talked about, are exceptionally good at catching sudden, sharp details. They detect the contours and edges gracefully. So when JPEG 2000 compresses an image, it preserves the smooth shapes and sharp edges without turning them into digital Lego blocks.
Right. And making this all run instantly on a standard computer required one more pioneer, Stefan Malland. He invented the fast transform algorithm, which made this complex math computable at lightning speed.
And Malland's contribution didn't stop at making images load faster. He recognized that the exact same mathematical clarity that wavelets brought to images was desperately needed in the biggest technological explosion of our generation, artificial intelligence.
And this brings us right back to Dr. Christophe Delong and the medical dilemma we started with, because we have two extremes in AI right now. First, you have the black box. These are massive deep neural networks that give highly accurate diagnoses, but nobody knows how they arrive at their conclusions.
And a doctor cannot ethically prescribe a life-altering medical treatment based entirely on a machine that simply says, trust me. There is no accountability.
Exactly.
So the alternative has historically been the white box AI. These are systems with simple, transparent, human-coded rules. You can see exactly how they think, but human biology is wildly complex. A simple list of rules is just too brittle to capture the chaotic nuances of a human body in motion.
So doctors are stuck between a genius they can't understand and an open book that just isn't smart enough to read the complexity.
Exactly. And Malat built a bridge between those two extremes with something called the scattering transform.
Okay, what is that?
Well, he had noticed something fascinating about those black box deep neural networks. When you feed them millions of images, their first layers naturally and spontaneously try to learn shapes that look exactly like wavelets.
Wait, really?
Yeah. The machine wastes enormous amounts of time and computing power just trying to organically invent the concept of an edge detector.
So the machine realizes that wavelets are the best way to see the geometry of reality, so it tries to build them from scratch.
Right. So rather than letting the AI stumble around blindly learning these shapes, Mallet decided to impose fixed wavelets right from the start. He said, let's build the front end of the AI using the scattering transform, which is essentially a cascade of wavelet filters.
Oh, wow.
And this creates a transparent, hierarchical decomposition of signals that a human expert can actually trace.
Let me see if I have this right. Is this like teaching a child physics by letting them drop a million apples until they vaguely understand the equation for gravity, which would be classic AI, versus just teaching them the equation for gravity from day one so they get it immediately?
You're close, but it's less about the equation for gravity and more about giving the child the fundamental concept of down before they even hold an apple.
Oh.
The AI isn't learning an equation, it's being handed a geometric dictionary of the physical world. And this approach, especially when applied to medical platforms like Kinexa, delivers 3 revolutionary benefits. The first is explainability.
And this is where Dr. Delong's work in biomechanics shines, right? Because when a patient walks across a force plate, Kinexa analyzes the gait.
Yes. And if the AI flags an anomaly in that walk, the black box becomes transparent. It doesn't just output pathology detected. Because it is built on wavelets, it can point backward through the mathematical layers and show the doctor, hey, I am flagging this because of a specific micro-oscillation at this exact high frequency, occurring precisely 0.4 seconds into the heel strike.
Well, it literally shows its work in time and frequency.
Exactly. And the second benefit of Mallet's approach is sobriety, which is tied to a concept you mentioned earlier, sparsity.
Sparsity, yeah.
Sparsity is a crucial concept here. Most data in the real world is redundant. Think of a blue sky in a photograph. It's just the same blue pixel repeated thousands of times.
Good.
Sparsity means cutting out all that massive redundancy and distilling a complex signal down to just a few critical defining numbers, the edges, the changes, the anomalies. Because wavelets are so good at finding sparsity, the AI needs vastly less data to learn. Standard AI might need millions of footsteps to understand a normal gait. Mallet's Kinexa system already knows the underlying physical geometry, so it learns with just a fraction of the data.
Which saves computing power, time, and, massive amounts of electricity. So what's the third benefit? You said there were 3.
The third is stability. Standard AI models are incredibly fragile. You change a single invisible pixel in a photo, and the AI suddenly classifies a picture of a cat as a school bus.
Oh, right. I've heard about that.
Yeah.
Gets tricked by high-frequency noise.
Exactly. But Mallet's models use a property called translation invariance.
Translation invariance. How does that protect the AI?
It means the AI can recognize the geometric shape of an anomaly, regardless of exactly when it happens or if it's slightly shifted. If an abnormality in a heartbeat happens a millisecond later than usual, a standard AI might get completely confused and misdiagnose it.
Oh, that's dangerous.
Right? But a wavelet-based AI recognizes the structure of the heartbeat itself. It's immune to small shifts in time or tiny amounts of static noise. In a hospital setting, that robustness isn't just convenient. It literally prevents catastrophic misdiagnoses.
So Mallet cracked the code. He made the math explainable, sober, and safe for human lives.
He did.
But as we get into the final part of our source material, things take a very unexpected turn. Because in the process of giving this pure, perfect math a human name, we actually created a philosophical trap.
Yeah, this is where we have to look at how we communicate science. Our source brings in the 20th century philosopher Ludwig Wittgenstein. He famously argued, whereof one cannot speak, thereof one must be silent. Wittgenstein believed language is not a perfect mirror of reality. It's a series of social games. Words only have meaning based on our shared human practices, not on some objective truth.
Wait, Wittgenstein, the philosopher, we were literally just talking about medical AI, biomechanics, and dot products. How on earth does a 1920s philosopher have anything to do with modern artificial intelligence?
It comes down to a trap mullet, and his predecessors accidentally set when they named their math. Our source calls it the treachery of abstraction. Think about the name Jean Morlaix chose on the let, or little wave.
Yeah.
By using that word, he appealed to human sensory memory. We all know what a wave in the water looks like. We understand the rhythm of the ocean. He humanized the math to make it intuitive.
Which is helpful for me, honestly. It gives me a visual.
And it is helpful for humans, but it polluted the pure abstraction. A perfect, raw mathematical equation was replaced by an imperfect metaphor. And when Mallet further developed the field, he created a whole dictionary of predictable tokens to explain it to humans. Words like wavelet, sparsity, multi-resolution, and translation invariance. He created a linguistic game to explain how the machine sees.
And this is where modern large language models, the AIs we use to write emails, draft essays, and chat today, get totally trapped. Because LLMs are fundamentally just giant text prediction engines. They devour words.
Exactly. We fed this entire dictionary of wavelet metaphors into the training data for modern LLMs. If you go to a chatbot right now and ask it to explain wavelet theory, it will generate miles of text that sounds incredibly mathematically intelligent, but it is just statistical word prediction.
The LLM is playing Wittgenstein's language game. It knows statistically that the word multi-resolution usually comes after the word wavelet, and that sparsity belongs in the same paragraph. But it doesn't actually understand the math. It has never performed a dot product. It has never experienced the mathematical reality behind those words.
Wittgenstein made a vital distinction between what can be said and what can only be shown. Wavelets show the structure of a signal directly through raw calculation. They calculate the numbers and reveal the hidden geometry.
Right.
Language, on the other hand, clumsily tries to tell you about it. The LLM can only tell. It parrots the metaphor of the little wave without ever doing the underlying calculation.
So by giving something a cute, relatable name, we actually distanced ourselves from the truth of the raw calculation. And the text-generating AI is completely trapped in that distance. It's wearing the clothes of intelligence without having the thought underneath. It's just predicting human metaphors.
Which is why our source ultimately emphasizes looking beyond the metaphors entirely. I mean, if we strip away the word wavelet, what is actually happening in systems like Kinexa? It is just a machine comparing numerical sequences via local correlation.
Wow.
It organizes reality by the speed of change, separating fast noise from slow underlying trends. It uses translation invariance to recognize shapes regardless of when they occur, and it uses sparsity to cut out the massive redundancy of real-world data.
No water, no ocean waves, just numbers checking for resonance. It separates the normal from the pathological without ever needing to use language.
And the raw mechanics are deeply beautiful in their stripped-down logic. It is a geometry of computation that gives us a transparent window into the invisible forces shaping our world, from the seismic echoes deep in the earth, to the compression of the photos on your phone, to the biomechanics of a patient taking a single step.
This has been such an incredible journey. I mean, from the blender of the Fourier transform to the sliding accordion of wavelets, to Dr. Delong and Kinexa building trustworthy medical AI, and finally to the limits of our own words. Thank you to everyone listening for joining us on this deep dive into the invisible mathematical reality of wavelets.
It's been great.
But before you go, I want to leave you with a final thought to mull over. Wittgenstein warned us that language disguises thought. If we are now building our future by training artificial intelligence almost exclusively on the vast oceans of our own metaphor-heavy language, will AI ever be able to truly understand the raw mathematical reality of the universe? Or is it doomed to be forever trapped inside the disguise of our words?